So we're going to learn about something called the Squeeze Theorem. All right. Some books call it the Sandwich Theorem. Some call it the Squeeze Theorem. I think both sound equally stupid. So I learned it as the Squeeze Theorem, so that's what I'm going to call it. All right. Let me get my calculator out. Put it in the right mode. Now, this is probably one of the most important limit concepts because what it does is it takes situations where you would look at and say, well, that's not something I can do analytically, and it provides you with an analytic approach. All right, so all those questions where you just had to assume that the limit was correct because the calculator told you so, we're actually going to figure out the reasons why they work the way they do. Right, so that's kind of cool, but I think the nice byproduct of that is I saved that for after the unit test. All right, I didn't want you to have to worry about doing this proof on the last unit test, right? Because it would be a little crunchy, right? But it's not terrible. So let me just talk you through it first. So it's saying that f of x is between two functions g of x and h of x, right? If that's the case, and its limit. The limit of f of x is between g of x and h of x. And also, this is the weird part, those two limits, g of x and h of x, are the same, then the limit of f of x is going to be the same as those two outer limits. All right? I said that really fast, but I'm going to show you the reason why I said it fast is because, like whether I give you the notation form or if I give you the verbal explanation, it doesn't really mean much without a visual. So that's what I'm going to do here. I'm going to show you the visual on this. First, I'll use a table approach, and then after that, I'll show you analytically how that works. So 1 divided by x plus 1. I'm going to look at the table for that. So I'm just going to change my table settings because when we're dealing with limits on the table, we want to have our settings the right way. So if it's approaching a constant, we want to have it start at the constant and some small value around that. If it's going out to infinity, then I would want to have some really large value for my change in table. So I'll put like 100,000 in there and see what happens. So I'll go into my table, and you can see, well, kind of, as I scroll down my list here, that these are scientific notation values that are incredibly small. All right, and getting smaller, getting closer and closer to 0. So it's a pretty safe bet that our limit's going to be equal to 0. All right. So that's how we approached this kind of thing before, but let me give you a sense of what it's really talking about. All right. I'll take a look at the graph. I'll just do a standard view. Now with this one, it's kind of weird because this is how we do standard view, but it is what it is. And I'm just going to focus on the positive end here. All right. So what I could actually do is create a function that I know is above, physically above the curve that I have here, and a function that I know is physically below it. And it's weird, like, okay, so isn't that like infinitely many possibilities? All right, there's a particular type. It's going to be related to the parent function. All right. You know it better as the end behavior model, all right? So that's what I'm going to do. I'm going to pop in just a 1 over x as another function and graph that. Now I'll bring it in a little bit closer so you can see. That red curve, I think pretty clearly, at least in the early going, is above the blue curve. But then eventually they start appearing as though they're merging. But that the relationship between those functions will actually never change. The red curve will always be on top of the blue curve. And that's because if I were to do this numerically, no matter what I put in for x, if I have 1 over x, that's always going to be a bigger number than 1 over x plus 1. All right? So another curve that I can put in, and we'll write all this out in a sec, but another curve I could put in would be the reflection of that one over the x-axis. So negative 1 over x. So I can graph that. All right. So just looking at this, let me just pop this in real quick. Hopefully you could see, as I've been saying, that that blue curve, which is the original one, is, I mean, I don't know that you'd use the term sandwiched, but it's in between the other two curves, the red and the purple one. All right. So we're going to flesh out, I'll put this in here so that we can mark it up. I'll just kind of pop that there. All right. So you could just do a rough sketch, but the red one is y equals 1 over x. The blue one was the given. You could write y or f of x, 1 over x plus 1. And the purple one was y equals negative 1 over x. So if you're a little iffy on where these are all coming from, like, I mean, this is all wonderful. How'd you come up with those functions? It's going to be made painfully obvious in a second. I'm going to give you a process. But it's a pretty safe bet that if, and this is an assumption, if the red and the purple are converging upon one another, right? If they're going to meet, then they're going to have the same limit eventually. All right, one's going to hit 0 from the bottom side, the other's going to hit 0 from the top side. If the blue one is trapped in between the red and the purple, then eventually it's got to have the same limit, right? Because if it's always going to be bounded between the red and the purple, and the red and purple are converging on 0, then the blue one must also converge on 0. All right, but what we need to do is prove that. All right, so you're thinking proofs, like geometry proofs. No, these aren't like that. Proofs, in fact, it's kind of crazy to think this. Proofs were never like that. They just, the statements and reasons columns that you created, that's just an organizational strategy. In real mathematical proofs, nobody ever structures it like that. It's always, here is the statement and the justification is immediately right after that. So it's more of a stream of consciousness kind of thing. The problem is, when you have 9th and 10th graders writing mathematics in stream of consciousness form, it becomes problematic in the grading department. So, statements and reasons. Anyway, what we do first is find the end behavior model. All right. So in this case, it's y equals 1 over x. And then you also want the negation of the end behavior model. So reflect over the x-axis, which it does not start with a y. X-axis. All right. That is the function, or the set of functions that your original 1 over x plus 1 will be trapped in between. So I'm going to create an inequality. One over x plus 1 is going to be in between negative 1 over x, and actually let me get rid of the equals, because it's more of a, I'll explain it in a second. It's in between negative 1 over x and 1 over x. You could actually put a less than or equal or a greater than or equal, less than or equal or less than symbol. It doesn't matter because the equality is an assumed equality. It's more of a theoretical thing. because the only time all three of these functions would ever be equal to one another would be if we got out to infinity. And so to say that it's equal at the moment, not true. But to say that it eventually be equal to one another, that would be true. So bottom line is, you can't go wrong either way. All right. So what we're going to do is find the limit of each of these as x approaches infinity. So we're going to indirectly find the limit of the inner function. Even though we did it plenty in the last unit, this is going to justify analytically why it worked the way it did. A nice little byproduct here is that you can, bless you, kind of take some things for granted. And that is, like in the last unit, you had to show me how you came up with the EBM, and then the substitution and things like that. I mean, you've already demonstrated knowledge on that. So now you could just jump right to, okay, well, what are these limits? What is the limit as x approaches infinity of negative 1 over x? 0. And on the high side? Same thing. All right. So it's in this step where you look at it and say, well, how could you have a number that's less than 0 and greater than 0 at the same time? Isn't that a contradiction? Well, that's what I was saying before. The functions themselves could not be equal in any way until they got out to infinity. So here, in this step, we're justifying that we're approaching infinity. So in this whole step, we're saying, okay, now we're leaving the technical, practical, and moving towards the theoretical. So if we are at infinity, like if infinity is a destination that you could get to, then the outer limits would be equal to 0. And so the inner limit would then be equal to those outer limits. All right, and then we would make the conclusion that the limit as x approaches infinity of 1 over x plus 1 would be equal to 0. All right, so that last little bit there is kind of strange because you look at it and say, well, yeah, but why did you, like, I understood you just said words, but how did you know you could make a less than into a less than or equal? And that is the theoretical component, because like if I'm looking at the x value of 2, so somewhere over here, x value of 2, that middle function is not equal in any way to the outer functions. But if I get out to infinity, so I'm all the way over here at infinity, then it is. So by applying the limit, I'm allowed to convert those less than symbols into less than or equal to symbols.
Quick reminder on how to find end behavior model. I feel like I'm mixing it up with another thing.
Take the term with the highest power on the top and divide it by the term with the highest power on the bottom, and then simplify. All right, in this case, it was simple, but it could be a little bit more complicated in other cases.
Like the next one, sin x.
Like the next one. Now, end behavior model doesn't apply for trig functions, so we have to use a different approach. All right, so that's the thing. The next two examples, we immediately depart from this idea, but then you can see in number 4, we bring the trig back together with what we were talking about in number 1. So let's investigate some trig cases.
Or it would be cosine x over x.
That could be part of it, but we're actually going to take a different approach. I'll show you. So what we can do, we could actually do a couple of things, but we can look at a function a piece at a time and say, all right, what do I know about this particular situation? Like, for example, I have a sine function. I'm just going to pull that out. So I'm not even gonna look at the graph. I'm just gonna take a fact that I know about a sine function, because we're working with the idea of betweenness here, all right? I just need to know two definite things that the sine function would be in between, two definite values that the sine function is in between. And actually, that sine function could be equal to those two definite values. If you don't know, oh, wrong calculator. I had the other one set up for another class. So let me pop in my sine function. I'll just do, if I were using a regular calculator, a zoom trig, but here I'll just hit graph. Can you see a definite value based on this graph that the sine function is between?
1 and -1?
1 and -1, exactly. We put the -1 on the low side. All right. Now remember, the sine function is a y. Y equals the sine of x. So we're looking for definite y values that it's in between. All right. Now, I can't just find the limit of this because it's not going to get the job done. If only that middle expression says sine of x over x. So what do you think I can do to this inequality to make that say the sine of x over x? Divide everything by x. All right. So now I can go to my calculator and verify that this is a true statement. Because that's the thing. You don't want to go on to the next step unless you know that this is legit. So sine of x over x, -1 over x, sine of x over x, -1 over x, and then +1 over x. We'll hit graph, take a look. Ooh, look at that. But if you kind of calm down the noise, you get a little better rendering of it. And aside from being just a generally cool looking diagram, it does justify the process we just used.
How do you like see that? Because mine is so small.
Try zoom trig, zoom 7. Oh yeah? Here, I'll take a quick look. If that doesn't work, then go into your window, make your y min and max -1 and 1, and then see if that does it. Did you get it?
I think I was doing something. You did something.
Hit Y. Hit and you're in rating form. Oh, that'll do it. Okay. All right, so it's pretty based on this diagram. I mean, you got to get to this diagram, but based on this diagram, it's pretty clear that the blue curve is sandwiched in between the purple and the red. So if I could just find the limit of the purple as it goes out to infinity and the red as it goes out to infinity, it seems like they're merging, then whatever the blue is, that's going to have the same limit. All right, so let's do that. So the limit as x approaches infinity of -1 over x is less than or equal to the limit as x approaches infinity of sine x over x is less than or equal to the limit as x approaches infinity of 1 over x. Now, some might wonder why it was okay to use a less than or equal to symbol right from the get-go on this particular problem, whereas in the last one it wasn't okay. And the rationale for that is we could actually get to the outer functions with the inner function, right? So there are moments along this curve where the sine of x over x is is equal to negative 1 over x, the red curve, it actually touches in a bunch of spots, and 1 over x, it actually touches in a bunch of spots. So there's no theoretical equality here, it's directly equal. And you get that if you don't recognize it based on the nature of trig, you get it just by looking at the picture. Now, we've already kind of investigated these, so we know outer is 0 in both cases, and so now we have our limit. All right, it's between 0 and 0, so I strongly suspect that the limit is going to be equal to 0. Now, I don't know where your calculus journey is going to come to an end. You know, this may be it, and you may have a bunch of years ahead of you. I don't know. But, well, so if this is it for you, then you're learning this for fun, okay? If you're going on to more calculus after this, this concept is going to come back repeatedly in every course that you take from here on out. Every calculus-based course. It always just like comes up. And so it'll be like, hey, we'll just apply the squeeze theorem here. And then you'll throw your hand up and you'll be like, quick refresher, squeeze theorem. And you'll be like, yeah, what's your question? What is that again? And then depending on how many people are in the classroom, that may be an okay question. You know, you're sitting in a lecture hall with 300 people. Be like, see me during office hours. But if it's a smaller class, you're going to a college where there's just not big classes, then it might be okay to have a brief refresher. So it all depends on the situation. Like in my classes, like I go over this in my Calc 3 class, so that's like 2 years after this. And so 4 calculus classes down the line, basically. And I go over these examples before getting into the Calc 3 related material. All right. So I'm going to leave you there. I'm going to let you struggle through numbers 3 and 4. It shouldn't be that much of a struggle, but I want you to try to do them on your own first before I spoil it all for you. So I'll throw a couple of stars on those bad boys for you. And also tackle the problems on page 2. They're not related to the squeeze theorem. They're just kind of seeing what you know related to graphical limits and piecewise and stuff like that. Sorry, let me turn off the video. So what you're looking for within each function is some reliable fact, all right? And so that reliable fact in number 3 is that the sine of 1 over x is going to be between negative 1 and 1. All right, and that's just because sine functions exist between negative 1 and 1. All right, if the amplitude was something other than 1, then that would be a different story. We're just looking to pull the relevant piece out.
Oh, I was going to ask about the x squared. You just drop it?
You drop it, at least in the first step, but then in the second step, we bring it back because we have our reliable fact. Now I can incorporate the x squared. I'm going to multiply that through, and that's going to give me negative x squared is less than or equal to x squared. Sine of 1 over x is less than or equal to positive x squared. All right. So then I'm going to find the limit of the whole thing. Little shorthand notation. All right. So when I write it like this, it's implying that I'm taking the limit of each part. All right. So the limit of my lower bound would be what? 0. What about my upper bound?
0.
Also 0. All right. So limit as x approaches 0 of x squared sine of 1 over x is less than or equal to 0. So that function has a limit that's in between 0 and 0 inclusively. And so that's what our limit's going to be. All right. And you could see how the notation could be a big issue on a question like this. All right. It's a proof, so everything has to be noted correctly. So if you lose your limits along the way, you lose inequalities along the way, it's going to cost you. All right. So you want to be careful about that. All right. Now, number 4, again, we have a reliable fact, and that is that the cosine function exists between -1 and 1. There's little shortcuts along the way that you might discover. In fact, there's a process you can use where we can actually use the entire 2 minus cosine of x. All right? And that's because 2 minus cosine of x has an amplitude of -1. So one thing you should consider is the calculator is a reasonable resource here. All right, so you've spent a lot of time over the last couple of years graphing trig functions, so it's not unreasonable to suggest that you could use that information to your advantage. All right, but let's say you didn't know that. I need a negative cosine x, so I'm going to negate the entire equation, or I'm sorry, compound inequality, in which case I'm going to get 1 greater than or equal to negative cosine x, greater than or equal to -1. All right, I'm going to add 2 to everything. So 3 greater than or equal to 2 minus cosine of x, greater than or equal to 1. In terms of the actual structure, I don't know if I want it to be like this, where the larger number's on the left-hand side, so I'm just going to reverse everything around. So 1 less than or equal to 2 minus cosine x, less than or equal to 3. Now, again, I'm trying to build towards the inner function. So I'm going to divide everything by x plus 3. And then I could apply my limit. And again, the legal shorthand notation is to just find the limit as x approaches infinity. All right? So I need to find the limit as x approaches infinity of each one of these. Now, something you have to consider is that this is a proof. All right? So you can't just really take it on faith that this is going to become just a 0 just because you want it to be. Just thinking back to number 1, we had to follow an entire process involving the EBM, and this is where it becomes a little bit more challenging because common sense is telling you that it should be 0, but you have to prove it. All right? So we need to go through this same process for each of these bounds. All right? So, well, I guess I don't need the double arrow. So this is really saying, if we go back to the same skill that we used yesterday, that 1 over x plus 3 is in between -1 over x and 1 over x. And that's because the parent function of 1 over x plus 3 is 1 over x. The negation of that is -1 over x. All right? Finding the limit of that as x goes to infinity tells us, if we're looking at each piece just by direct substitution, we know that those are going to 0. So I can conclude that the limit as x approaches infinity of 1 over x plus 3 is equal to 0. All right? Now, by extension, I could also conclude that the limit as x approaches infinity of 3 over x plus 3 is also going to be 0, because that's just a constant multiple away from being the limit as x approaches infinity of 1 over x plus 3. So that one we could kind of jump to. So these are our justifications for saying that on the low ends we have 0. And so this limit of the whole shebang, 2 minus x, cosine x over x plus 3, is going to be equal to 0. Now, it's kind of annoying, frustrating, I get it, because you look at this and say, well, I can get this from the calculator, I got the gist of it, all that stuff, but it's a rigorous proof. And so when you're proving something, all the little details need to be there. So the feeling shouldn't be too hurt if you eliminate a step or two and you lose credit for your omission, you know, like that's just how it is, you know.
So you do have to separate those each, like you can't just do it like, just know they're gonna be 0 every time like you did with 3.
Yeah, because in this one, it's direct substitution. If I replace an x squared with a 0, it becomes 0.
Right, there's no EVM.
Right, exactly. It's its own EVM. Alright. Yeah.
So like you lose points, like on the last one you didn't show all the work for it. You lose points for not doing that.
Yeah, because it's a proof.
Okay.
Yeah. If it just said find the limit, we wouldn't do any of this. You just look at the calculator.
Okay, can't you just plug infinity into the denominator again and two is just
Yeah, but then the question is, what's infinity plus 3? You know.
Infinity.
Theoretically, we assume that, but we know that 1 over infinity is 0 based off of the end behavior models. We can't, since we can't get to infinity, we can't go beyond it.
so if you do for 1/2, you don't do the other.
Yeah, and that's only because it's only a constant multiple of 3. Because really all you'd end up doing is factoring out a 3 from the whole thing and you get the same exact work. So there's no need to do it a second time.